There's a moment in Interstellar that breaks your brain. Cooper and his crew are drifting through space. Ahead of them, there's something. A sphere. A perfect shimmering sphere floating near Saturn. Not a planet. Not a star. Something that shouldn't exist. They fly into it, and somehow, impossibly, they emerge on the other side of the galaxy, 10 billion light years from Earth. In seconds. Wait, what? Light takes years to cross that distance. Our fastest spacecraft would need millions of lifetimes, fully explains. Was that wormhole a real shortcut through space? Or was it something else entirely? A beautiful illusion that physics would never actually allow. Because here's the uncomfortable truth. The scientist who helped design that wormhole for the film Kip Thorne knew something most viewers didn't. Wormholes might exist. But surviving one? That's a completely different question. And the answer is terrifying. Picture this. You're Cooper, former NASA pilot, farmer now because the world is dying and someone has to grow corn. You've spent years watching dust storms bury your home, watching crops fail, watching humanity slowly give up on the stars. And then somehow you end up here, sitting in a spacecraft called the Endurance, drifting through the blackness near Saturn. You've been traveling for 2 years just to reach this point, 2 years in a metal box, knowing that every mile takes you further from your daughter, from Murph, from the promise you made to come back. But none of that matters right now, because ahead of you, there's something that shouldn't exist. It looks like a sphere, a perfect, impossible sphere hanging in space. Not solid, not empty, something in between. Light bends around it in ways your eyes can't fully understand. Stars behind it appear warped, stretched, duplicated. It's like looking at the universe through a glass marble filled with darkness. Your crewmate Romilly tries to explain it. He takes a piece of paper, folds it, pushes a pencil through both sides. A wormhole, he says, a shortcut through space-time. Simple enough, right? Except nothing about what you're seeing feels simple. The Endurance moves closer, the sphere grows larger, and then you're inside it. This is the part that in minutes, the crew celebrates. You've made it. The mission can continue. There's hope, but you can't stop thinking about what just happened, what you saw, what you felt. Because here's the thing, you're a pilot. You understand physics. You know that what you just experienced shouldn't be possible. Distance is real. Space is real. You can't just skip across the universe like jumping over a puddle. And yet, you did. So what actually happened inside that sphere? Was it really a shortcut, or was it something else entirely? A trick of light, a bending of reality, an illusion so convincing that even physics seemed to agree with it. The movie gives you an answer, but physics has a much stranger story to tell. Let's step out of the movie for a moment. Let's talk about you. You've lived your entire life on a small rocky planet, spinning around an average star in a quiet corner of an average galaxy. Everything you've ever experienced, every trip you've taken, every distance you've measured, has followed a simple rule. Getting somewhere takes time. Walk to the store, 5 minutes, drive to another city, a few hours, fly across the ocean, half a day. The further the destination, the longer the journey. It's so obvious that you don't even think about it. It's just how things work. And this assumption runs deeper than you realize. Your brain, without you even noticing, has built a model of the universe based on your everyday experience. Space is like a giant empty room. Objects exist in fixed locations. To get from point A to point B, you have to cross everything in between. There are no exceptions. This is why the folded paper analogy feels so satisfying. You've probably seen it 100 times. Someone holds up a flat sheet of paper. This is space, they say. Then they fold it so two distant points touch. If you could bend space like this, you could take a shortcut. They poke a pencil through both sides. A wormhole. Simple. Elegant. Makes perfect sense. But here's the problem. That analogy is designed to comfort you. It's designed to make the impossible feel intuitive. And in doing so, it hides something crucial. Space isn't a piece of paper. You can fold paper because paper exists in three-dimensional space. You can bring 2 points together because there's a direction to fold it in. Up, off the table, into the air above. But space itself, what would you fold it into? Space is already everything. There's no outside of space. No extra dimension waiting conveniently for us to exploit. At least not one we've ever detected, not one we can access. So when Romilly folds that paper in the movie, he's showing Cooper something that makes emotional sense, something that feels logical. But he's not showing him reality. The real story of wormholes isn't about folding. It's about something far stranger, something that requires you to abandon the model your brain has spent a lifetime building. And most people never get there. Most people watch that scene, nod along, and think, got it, space folds, wormhole, shortcut, makes sense. It doesn't make sense. Not yet. Because to understand what a wormhole really is, if it really is anything, you need to understand something Einstein figured out over a century ago. Space isn't empty, it isn't passive, and it definitely doesn't play by the rules you think it does. The year is 1915. Europe is at war, empires are crumbling, millions are dying in trenches, and in Berlin a German physicist with wild hair and a cluttered desk is about to change everything humanity understands about reality. His name is Albert Einstein, and he has a problem. For years he's been wrestling with gravity. Newton's version, the one you learned in school, works beautifully for apples and planets. But Einstein knows something is wrong with it. Newton described gravity as a force that pulls objects together across empty space, instantaneously, magically, without explanation. Einstein doesn't believe in magic, so he asks a different question. What if gravity isn't a force at all? What if it's geometry? Here's what he figured out. Space and time aren't separate things. They're woven together into a single fabric, space-time, and massive objects don't pull on other objects. Instead, they bend the fabric around them. Imagine a bowling ball on a stretched bedsheet. The ball creates a dip, a curve. Now roll a marble nearby. The marble doesn't get pulled toward the bowling ball, it just follows the curve in the sheet. It's moving in a straight line, but the sheet itself is bent. That's gravity, not a force, a shape. Einstein publishes his theory. It's called general relativity, and almost immediately other physicists start exploring its implications. One of them is a German soldier named Karl Schwarzschild. Schwarzschild is literally fighting in World War I, calculating artillery trajectories on the Russian front, when he reads Einstein's paper, and somehow between battles, he solves Einstein's equations for a single massive object. His solution describes something strange. If you compress enough mass into a small enough space, space-time doesn't just curve, it ruptures. A point of infinite density, a hole in the fabric itself. We now call this a black hole. But here's what most people don't know. Schwarzschild's math contained another secret, a hidden structure, a possibility that even he didn't fully explore. What if the hole wasn't just an ending? What if it was a passage? Decades later, physicists would find this buried in the equations. 2 points in spacetime connected by a tunnel through the geometry itself, not folding space from the outside, but creating a bridge within the fabric. Einstein himself studied this with his colleague Nathan Rosen in 1935. They called it an Einstein-Rosen Bridge. Today, we call it a wormhole. Einstein's equations said it was mathematically possible. The geometry allowed for it. The numbers worked out. But Einstein never believed it was real. He thought it was just a quirk, a mathematical curiosity, a structure that could exist on paper but never in the actual universe. And for decades, most physicists agreed with him. But here's where it gets strange. Einstein's equations allowed for wormholes, but Einstein himself never believed they could actually exist. Why? Because something deadly hides inside them, something that collapses faster than light itself. And to keep a wormhole open, you'd need something that might not exist anywhere in the universe. So let's pause here. Einstein's math says wormholes are possible. The geometry checks out. The equations balance. On paper, you can draw a tunnel connecting two distant points in space-time. Beautiful, except for one devastating problem. That throat wants to pinch shut. Gravity pulls it closed from all directions. The walls race toward each other at nearly the speed of light. If you tried to enter, you wouldn't make it through. You'd be crushed, stretched, annihilated. Somewhere in that collapsing tunnel, your atoms would be smeared across dimensions that emerges intact, calm, ready for the next mission. Physics laughs at this. The real wormhole, if it existed, would kill him before he crossed the threshold. So how did the filmmakers get away with it? This is where things get theoretical. Desperate almost, because physicists knew about this problem for decades, and the only solution they could imagine required something extraordinary. Exotic matter. Not antimatter, not dark matter, something even stranger. A substance with negative energy density, a material that pushes instead of pulls, that repels gravity instead of creating it. If you could line the throat of a wormhole with exotic matter, you might might be able to hold it open. The negative energy would counteract the collapse. The walls would stabilize. The tunnel would remain passable. There's just one problem. We've never found exotic matter. Not a single particle. Not one confirmed observation. It exists only in equations and speculation. Some physicists believe quantum mechanics might allow for tiny amounts of it. Microscopic fluctuations in empty space that briefly exhibit negative energy. But even if that's true, the amount needed to stabilize a wormhole would be incomprehensible. We're talking about energy magnitudes that dwarf everything humanity has ever produced, combined. So where does that leave us? The wormhole in Interstellar is theoretically possible, mathematically consistent, visually accurate, according to Kip Thorne's calculations. But physically real? That's a different question entirely. And the movie quietly sidesteps it. Cooper asks, who created the wormhole? Who placed it near Saturn? The answer is vague, mysterious. They. Because the filmmakers knew the truth. No natural process we understand could create a stable wormhole. If one exists, something, or someone, would have to build it. All right, let's go deeper. Forget the movie for a moment. Forget Cooper and Murph and the emotional music. Let's talk about what a wormhole actually is. Not the analogy, not the folded paper, the real thing. First, you need to abandon a comfortable idea. You think of space as emptiness, the void between planets, the black background behind stars, a big empty room where stuff floats around. That's wrong. Space is a thing, a physical, measurable, bendable thing. It has shape, it has structure, and according to general relativity, it responds to mass and energy like a fabric responds to weight. Now imagine that fabric stretching infinitely in all directions, 3 dimensions of space, woven together with 1 dimension of time. Space-time. A wormhole isn't a tunnel through this fabric, it's a tunnel in this fabric, a geometric structure. 2 separate regions connected by a throat that exists within the mathematics of space-time itself. Here's an analogy that works better than folded paper. Imagine an ant walking on the surface of an apple. The ant can only move forward, backward, left, right. It doesn't know up or down exist. Now imagine the apple has a wormhole, literally a tunnel eaten through the center. The ant could walk around the apple's surface the long way, or it could enter the tunnel and emerge on the opposite side in a fraction of the time. From the ant's perspective, the tunnel is a shortcut, but the tunnel isn't folding the apple. It's not bending anything, it's just there. A different path through the geometry. This is closer to what a wormhole actually is. Not folding space, not bending it from outside, but using the hidden geometry of space-time itself to connect points that seem impossibly far apart. Now here's where Kip Thorne enters the story. When Christopher Nolan approached Thorne about Interstellar, he didn't just want a cool-looking effect, he wanted accuracy. He wanted a wormhole that reflected real physics as closely as possible. So Thorne ran the numbers. He calculated what light would actually do near a wormhole, how gravity would bend photons, how stars on the other side would appear, distorted, duplicated, smeared into rings of light. The visual effects team built their software around his equations. The result? That shimmering sphere Cooper sees wasn't artistic imagination. It was physics rendered on screen. The lensing effect, the distortion, the strange reflections, all mathematically derived. And here's the number that matters. To keep the wormhole in the film stable and traversable, Thorne calculated it would need to be about 2 kilometers wide, roughly 1.2 miles. And the energy required to hold it open? Approximately the total energy output of 1 billion suns, 1 billion stars, all their light, heat, and radiation combined, just to keep a tunnel open for a few minutes. That's not a technology gap. That's an impossibility gap. A civilization would need to harness energy on a scale we can barely imagine. But the real question isn't whether wormholes exist, it's whether they're shortcuts at all, because some physicists believe you could enter a wormhole, travel through it, and arrive before you left. Not just crossing space, crossing time. And if that's possible, then every paradox you've ever heard of, killing your grandfather, meeting yourself, changing history, becomes terrifyingly real. The shortcut might not just be dangerous, it might be forbidden. Let's slow down. We've talked about geometry, energy, collapsing throats, and exotic matter, but underneath all that physics, there's something else, something more human. Why do we want wormholes to be real? Think about it. We've never found one. We have no evidence they exist naturally. The energy required to build one exceeds anything our species could produce for millennia. And yet, we keep imagining them, writing about them, making movies about them. Why? Here's the uncomfortable truth. We are alone. Not in the aliens don't exist sense, in the cosmic sense, in the sense that the nearest star system is 4 light years away, in the sense that even traveling at impossible speeds, exploring the galaxy would take thousands of generations. The universe is vast and empty and slow. We are trapped, not by walls or chains, by distance itself, by the fundamental structure of space-time, by the speed limit written into reality's source code. Light travels fast, but not fast enough. A message to the nearest star takes 4 years. A reply takes 4 more. A conversation would take a lifetime. A journey would take centuries. And somewhere deep in the human psyche, this terrifies us. We evolved on a small planet. We learned to explore, to migrate, to spread across continents and oceans. Movement is in our DNA. The idea that we might never leave our cosmic neighborhood, that we might be born, live, and die in the same tiny corner of an infinite universe. It feels like a prison sentence we didn't earn. This is why wormholes matter, not because they're scientifically likely, but because they represent hope, a door in the wall, an escape hatch from our isolation, a whisper from physics that maybe, just maybe, the universe isn't as closed as it seems, and this is what Interstellar understands so deeply. Cooper doesn't enter that wormhole because he's curious about physics. He enters it because he's desperate, because Earth is dying, because his daughter needs a future, because love, stubborn, irrational, human love, refuses to accept that distance should separate families forever. The wormhole isn't just a plot device. It's a symbol, a prayer, a scientific miracle that represents everything we wish were true about the cosmos. We want shortcuts to exist because the alternative, accepting that we're stranded here forever, is too painful to bear. All right, time for the payoff. You've seen the movie. You've heard the physics. Now let's put them side by side and ask the uncomfortable question. What did Interstellar get right, and where did it quietly lie to you? Let's start with the good news. The wormhole's appearance, remarkably accurate. That shimmering sphere Cooper approaches isn't some artist's fantasy. Kip Thorne's equations predicted exactly what light would do near such an object. Gravitational lensing would bend photons around the throat. Stars behind the wormhole would appear distorted, stretched into rings. Light from the destination galaxy would leak through, creating that eerie glow. The visual effects team at Double Negative spent over a year rendering these calculations. Some frames took up to 100 hours each to compute. The result was so scientifically precise that Thorne later published academic papers based on the simulations. So visually, the movie nailed it. But here's where things fall apart. The experience of traveling through? Pure fiction. Remember Cooper floating calmly through the wormhole, touching hands with some mysterious presence, emerging unharmed on the other side? In reality, that journey would be catastrophic. First, there's tidal forces. Near any massive gravitational structure, gravity pulls harder on the parts of you closest to the center than the parts further away. Near a wormhole's throat, this difference would be extreme. Your body wouldn't just feel uncomfortable, it would be stretched, pulled apart atom by atom. Physicists have a term for this, spaghettification. You would become a stream of particles before you reach the other side. Second, there's radiation. Wormholes, if they exist, would likely accumulate intense electromagnetic energy around their throats. Light falling in from both ends would blue shift to lethal frequencies, gamma rays, X-rays. You'd be irradiated thousands of times over before the stretching even began. Third, there's the collapse problem we discussed earlier. Without exotic matter holding it open, the wormhole's throat would slam shut faster than you could traverse it. The tunnel would become a crushing vice, squeezing you into dimensions that don't have names. The movie shows none of this. Cooper experiences some turbulence, some visual distortion, a moment of wonder. Then he's through. Easy. Why the difference? Because the filmmakers faced a choice. Scientific accuracy, which would mean instant death in a very short film, or narrative survival. They chose story. They chose hope. They chose to let Cooper live so the emotional journey could continue. And honestly, that's fair. Interstellar isn't a documentary. It's a myth dressed in physics clothing. The science is scaffolding for something bigger, a story about love, sacrifice, and humanity's refusal to accept limits. But you should know the truth. If wormholes exist, And that's still a massive if. They would not be doorways. They would be death traps. The most hostile environment imaginable. A place where every force in the universe conspires to annihilate anything that dares enter. The film's Wormhole required the energy of 1 billion suns to remain stable. A real wormhole might require something we can never provide. And even if we could, survival might still be impossible. So where does that leave us? With a beautiful lie, a gorgeous, scientifically inspired lie that lets us imagine a universe more navigable than the one we actually inhabit. The movie gave us the dream, physics gives us reality, and the gap between them, that's the space where hope and heartbreak live together. So let's return to where we started, that sphere near Saturn, that impossible doorway, Cooper flying through, crossing the universe in minutes, emerging alive on the other side. Was the wormhole a shortcut, or was it an illusion? Here's the answer, and it's not simple. Mathematically, wormholes are real. Einstein's equations allow for them. The geometry exists. The physics is consistent. If you could somehow create one and somehow keep it open, you could theoretically connect two distant points in space-time and cross between them faster than any conventional journey would allow. In theory, yes. Wormholes are shortcuts, but in practice, they're closer to miracles. We've never observed one. We don't know if they form naturally. The energy required to stabilize one exceeds anything our civilization can produce. And even if we solved all those problems, the environment inside might be unsurvivable. The movie showed you a door. Physics shows you a door that's locked, on fire, surrounded by radiation, and possibly imaginary. But here's what I keep thinking about. Interstellar ends with Cooper, reunited with Murph. An old woman now, bad decision, and he's still young because of time dilation. They have a moment, a goodbye, and then he leaves again, heading back through the wormhole to find Brand, the woman who's alone on a distant planet, starting humanity's new beginning. He chooses to cross the universe again, knowing what he knows, knowing what it costs. Why? Because the alternative is staying still, accepting the distance, letting the universe keep its prisoners, and maybe that's the real point. Wormholes might not exist. Shortcuts through space might be forever beyond our reach. We might be trapped in this tiny corner of the cosmos for the rest of human history. But we keep looking, keep dreaming, keep writing equations and making movies and refusing to accept that the walls are permanent. The wormhole in Interstellar isn't just a plot device. It's a statement of faith, a belief that the universe, despite its vastness and hostility and silence, might still have doors we haven't found yet. And here's the question I'll leave you with. If the universe placed these doors in the fabric of reality, these mathematically possible but physically impossible tunnels, were we ever meant to open them? Or is the distance itself the point? Before we end, there's one more story worth telling. It's about Kip Thorne. You've heard his name throughout this video. The physicist who designed Interstellar's wormhole. The man who made sure the science was real, or as real as theoretical physics allows. But here's what most people don't know about him. Thorne didn't just consult on the movie. He spent years thinking about wormholes before Hollywood ever called. He wrote papers about them, argued about them, wondered if they could ever be made real. And he made a bet. In 1974, he bet Stephen Hawking, yes, that's Stephen Hawking, about whether black holes destroy information. It was a friendly wager, but it represented decades of scientific debate. Two giants pushing each other toward truth. Hawking eventually conceded, paid his debt with a baseball encyclopedia. But here's the point. These men weren't just calculating. They were wondering, dreaming, playing with ideas that might never be proven in their lifetimes. That's what physicists actually do. They don't sit in cold labs confirming what's already known. They chase the impossible. They ask questions that sound like science fiction. And occasionally, very occasionally, they find answers that change everything. Thorne won the Nobel Prize in 2017, not for wormholes, but for detecting gravitational waves, ripples in space-time itself, caused by colliding black holes a billion light years away. The universe bends, it ripples, it responds to mass and energy in ways we're only beginning to measure. If space-time can wave, can it also tunnel? Thorne doesn't know. Nobody does, but he spent his life asking. And when Christopher Nolan came to him with a movie about hope and desperation and crossing the uncrossable, Thorne didn't just check the math, he poured his wonder into it. Every frame of that wormhole represents decades of questions, a lifetime of staring at equations and asking, what if? That's the human story behind the physics. Not certainty, not arrogance, just endless, stubborn curiosity. And maybe that's what makes us human in the first place. We see the impossible, And instead of looking away, we ask, how? So what have we learned? We started with a movie scene, a sphere near Saturn, a crew flying into the unknown, and we asked a simple question. Are wormholes shortcuts or are they illusions? Now we have the answer. They're both. In mathematics, wormholes are elegant, real structures permitted by Einstein's geometry, tunnels through space-time that could, theoretically, connect the unconnectable. In physics, they're nightmares, collapsing, hostile, energy-hungry structures that would destroy anything attempting to pass through. Possible on paper, impossible in practice, and in our hearts, there's something else entirely. They're symbols, representations of our deepest longing, to escape our isolation, to reach the unreachable, to prove that love and determination can overcome even the architecture of the universe itself. Interstellar understood this perfectly. It gave us accurate physics wrapped in emotional truth, a wormhole that looks real because the math is real, a journey that feels possible because we desperately want it to be. The film doesn't lie to you. It invites you to hope. And maybe that's enough, because here's the thing about science. It doesn't just tell us what's true. It tells us what's possible. And sometimes, in the gap between the known and the unknown, it tells us where to dream next. Wormholes might never exist. Or they might be everywhere, hidden in dimensions we can't perceive. We don't know yet. But we're asking. Every day, physicists around the world are pushing equations, testing theories, staring at the fabric of reality and wondering if there's a door we haven't found. And that's the legacy of movies like Interstellar. Not that they show us truth, but that they remind us to keep looking for it. The universe is vast, cold, silent, indifferent, but we're still here, still dreaming, still reaching. And that's not physics, that's human.